so oh, there is some fire alarm. Yeah,
Oh
fire
no!
alarm.
Do you have to run?
No, I think it's
The drill. Is
a
it
drill.
drill?
Yeah. So, but I hope they don't come and try to get me anyway. Anyway, so yes, thanks very much for the invitation. What I want to do today is tell you a little bit about the things that I've been working with some collaborators here at the IIS. Misha Ivanov is now at the IIS. Oliver Philcox is a student at Princeton, and Marko Simonovic was here at the IIS, but has since moved for a while now. He's at CERN. So okay, so large-scale structure. So the distribution of matter in the universe today on large scales, it's complicated and encodes a lot of information about our cosmological model, properties of the dark matter, or the expansion history of the universe. They are all encoded in the distribution of matter that we can see in the universe today. On small scales, this distribution of matter is quite complicated. Matter tends to form objects like galaxies and clusters of galaxies, and eventually stars and planets, etc. Those are complicated to model and to extract cosmological information from them. But if we step a little bit back and look at the larger scale distribution of matter, then this still encodes information about some basic properties of cosmology in a similar way as the cosmic microwave background does. Now, as you go to smaller and smaller scale, modeling the distribution of matter becomes more and more complicated. There's many different physical effects that affect it, including when we make these maps of, what you can see here on the left is a depiction of various maps of the distribution of nearby or relatively nearby galaxies, where the radial distance is gotten through the redshift, the Hubble law. And so this is affected by so you're really measuring redshift. So the radial distance is not actually distance, but it's actually includes also some information about the peculiar velocities, which also the motions of things then. So when you make maps of the nearby universe, you not only can infer the density, how roughly speaking, the matter is distributed, the density of the matter nearby, but also how it's moving, because the peculiar motions along the line of sight affect the redshift. And so all of that, and the basic cause of the motion is gravity, and so it's another window into how matter is distributed. One of the ways to map the structure of matter around us is, I was saying, looking for look at some tracers. So, for example, galaxies. Look how galaxies are distributed, and we use redshift surveys to measure the location and in the distance of these galaxies. And so here is a plot from some white paper written by this mega mapper project that was proposing to the decadal survey here in the United States, summarizing a little bit the history of redshift surveys that shows the year and the number of redshifts that, so basically the number of galaxies that various redshifts throughout the years were able to gather. And the current time, the survey that is taking data now, it's called DESI, and it's the data that already existed is public, and you can analyze, and from which we get some of these cosmological constraints, is what's called here BOSS. This new DESI survey will be, an order of magnitude improvement, or a little bit more perhaps, in the number of redshifts, and it's already taking data. It takes the data at a tremendously high rate, like 100,000 redshifts per night, something like that. So it's just a completely different ball game. So this just to say that we expect in this line of of inquiry a lot of new data in the near future, and even in the even as we go further, there are ideas of how to make an even bigger leap. So what we want to use these surveys for, we want to understand, so they encode, as I was saying, properties about the expansion history of the universe, so you perhaps can get a sense of the evolution of the dark energy. They might encode information about properties of the dark matter or the neutrino masses, for example. And also the properties of the initial conditions that lead to the structure formation. So things related to the Gaussianity of the distribution of the initial conditions. All of these things are things that you can imagine probing with these upcoming surveys. And I guess dark energy is perhaps the focal point of at least the next generation of surveys. But there's also the question of trying to use these surveys in addition. When you look at the current state of the cosmological model, there are various hints of potential tensions between the results of different experiments, which hopefully they might be pointing to new physical effects, or they might be pointing to some a systematic problem in the measurement. So that's another thing that we hope to iron out with the addition of new data. The two well-known tensions in the cosmological model. One is about the value of the Hubble parameter, the difference in the Hubble parameter as inferred from the cosmic microwave background, which is the first point in this slide because it says Planck. And one of the versions of the direct measurements from type 1a supernovae and Cepheid, it's called SHU. So those are kind of in tension. The other tension that exists in a variety of data sets when compared to the CMB, large-scale structured data sets when compared to the CMB. Here I put some examples from weak lensing measurements from DES. Is a measurement of the amplitude of clustering. So this parameter sigma 8 measures the size of the fluctuations of this matter distribution as measured, say, by weak lensing or large scale, or the distribution of galaxies depending on the probe. And there's some tension in that the value that is inferred from the CMB, which is the last point in this summary here, tends to be larger than what, say, it's inferred by several. It's typically the case that these large-scale structure probes, this plot is from one particular example, but look at the top point, for example, tends to be lower than the value given by the CMB. None of these tensions at the moment are, one can debate whether or not they point to new physics, they point to systematics, they could be just still be a statistical fluke. So this is the kind of the state of the field right now. So, but my focus of the talk today is on large scale structure. So as I say, there are many open questions in cosmology. In the case of I already mentioned them. And we think that to answer some of these questions, studying the clustering of matter on large scales in the nearby universe through, for example, galaxy surveys will provide a significant amount of information. As I was saying in some of the first slides, as you go to small scales, the distribution of matter becomes complicated to model. But as it turns out, a lot of this cosmological information, and in fact, a lot of the statistical power of these surveys resides on scales that are pretty large, that are the dynamics is rather simple, it's almost captured by linear theory, but not quite. There are small corrections that one can try to understand and compute. These corrections are small, but however, they are much larger than the very small errors that these future surveys and current surveys are going to have. And so it's a regime in which some sort of analytical type of treatment can work very well, because on the one hand, it's the dynamics is rather simple, almost linear theory with small corrections, and you also need to track these small corrections very precisely, because the error bars are indeed very small. And so the basic question that I've been working on for some time is to try to understand what is the detailed theory, dynamical theory, that actually describes the evolution of the universe on these large scales, taking into consideration consistently the effects of the small scale dynamics that is more complicated, but it's on scale smaller than the one that you are measuring. And so these more complicated dynamics really changes the large scale theory, and also changes the large scale theory. You can think of it that the random motions on small scales of matter lead to an effective viscosity and sound speed, things of this nature. So even though you think of dark matter as a very cold fluid, now that you look at it on large scales in the context of these very small scale motions that are there due to the complicated objects that have already formed, the theory itself is that of a more complicated fluid. But in addition to just trying to understand that, there's the connection between the distribution of matter and the tracers that you actually observe. At the end of the day, we are measuring galaxies, so you need to make a connection there. And that is also a connection that is complicated to model, or impossible perhaps to model from first principles, and that we need to incorporate in this theoretical program in such a way that it can be done accurately enough that it can survive these very small error bars that we have now, and that we will have even more in the future. So as an example, this plot over here shows the 2-point correlation function of matter at some low redshift, probably redshift around 0. And it shows the dark line is just the linear, what the linear theory would predict. That's a function of, this is the 2-point correlation function in Fourier space. The x-axis is the wave vector in inverse megaparsecs. The y-axis is the 2-point correlation function. The prediction from linear theory is the dark line. The dashed line is a measurement, is a estimate of the typical noise that you would have in one of these surveys. So you would see, because we are tracing the distribution of matter with discrete objects like galaxies, so there is some level of what we call shot noise. And you can see that on the higher case here, the noise dominates over the signal. And then you can see the corrections to this linear theory that you can compute perturbative. For example, the first correction, the next to leading order contribution is the dashed blue line, and you can see that it's a small on the scales where the signal dominates over the noise. This is a small correction, so the perturbative approach makes sense. But the dots kind of show you the typical error bars that you might expect from surveys like the ones we have now. And you can see that it's still the case that these corrections are much bigger than the error bars. So you need to be able to compute them. It's not that you can be ignored. So the dynamics cannot be just described by a linear theory, which is what we use in the cosmic microwave background. However, it's still in a regime where the corrections are small. So there is a small parameter to do perturbations and keep enough terms to be below these dotted points. So that's the program that we've embarked in for quite a while now. So this is the so-called effective theory large-scale structure, and effective is alluding to the fact that on large scales, the fluid that you are solving for, of the matter that you're solving for, is not a cold dark matter, but it's a fluid that has additional properties, and that are imposed on you from the fact that you are kind of integrating out the small scale dynamics. So it's just a theory that describes, but it's a well-defined theory. You can write down, integrate, in some sense, integrate out the small scales, see what those effects are on the dynamics on large scales, and it produces for you a bunch of like equivalent to a viscosity and so on that you could have to keep track, but it's all well defined, and in principle, to get a given accuracy, you know how many orders in your perturbation theory you need to do. And so so this is a framework to describe what's happening on large scales, but I argue that that's where a lot of the information, at least in the galaxy redshift surveys, lies. And it, you know, it's the dynamics on large scales is more complicated than just that of a cold dark matter, say. And so there are some free parameters in this theory that encodes that result from the integration of the small scale. So you have to keep track of them and somehow fix them but they're just numbers, and we are measuring full curves as a function of, like, the 2-point correlation function as a function of wave number, and we are also measuring higher order moments, etc. So and this we need to fix a few free parameters that we cannot determine from first principles. Some of them you could determine, for example, from numerical simulations at some level, or at least have a good sense of their typical sizes, but in detail for the redshift surveys, because we do not we measure the positions of galaxies that are complicated objects which we cannot model from first principles. We can get a sense of the values of some of these parameters from simulations that try to form galaxies, but we can never be sure, especially with the level of error bars that we have, that those are, we cannot just plug in the numbers that we get from simulations. So this still needs, is still a major source of uncertainty in all our cosmological inferences, trying to understand the effects of the connection between galaxies and matter, and etc. Like, typically called these bias parameters. So in reality, the constraints that we get on cosmological parameters of interest are significantly degraded by the fact that we need to get constraints on these connection nuisance parameters, like the biases and viscosities and so on of this theory. These plots over here just are illustration of the fact that you really pay a big price for not having a first principle theory of the connection, say, between matter and galaxies. So let's just focus, for example, on the left plot. This shows the error bars that you can attain on various cosmological parameters of interest. Let's just focus on the top plot, which is for the Hubble parameter, the Hubble constant. If you have a survey that measures the power, the 2-point function up to a given wave number k, which is the x-axis, it shows you the error bar that you would get on those parameters. And the three colors, blue is what you would get if all that you were trying to determine was the Hubble parameter, and everything else was known to you. In the green, it's the effect of having yet to marginalize over the uncertainty of all the other cosmological parameters that we don't know. So that, at some level, it's okay because we are interested in getting those cosmological parameters. But then you jump to the red when you have to marginalize over these nuisance parameters that are related to uncertainties that, say, for example, in the galaxy formation processes. And so you pay quite a big price by the time you go to high Ks by this marginalization. You can look in all the plots, is the same. And the right panel shows a similar kind of situation. So okay, so we've in the last few years we've been trying to make progress on this theoretical framework in various ways, but also lately we have been directly using it ourselves to get constraints on cosmological parameters from existing public data to test our models and see if they are first of all, what we can learn at this point, and also eventually also we have also been testing them for their application to future surveys, for example, to see if they stand to the test of these very small error bars. An example of this is something we managed to get was a direct measurement of the Hubble parameter from data from the BOSS survey with an error bar of around 1%, which is independent of the cosmic microwave background measurements. So the way this works is that the objective of this BOSS survey was to measure these so-called variant acoustic oscillations, which are wiggles in the 2-point correlation function, which are the equivalent or the analog of the oscillations that you see in the cosmic microwave background power spectrum. If instead of looking at the 2-point function in Fourier space, you look at the 2-point function in the real space, in configuration space, the 2-point correlation function has a little bump around 100 megaparsecs, and that serves if you know this physical scale where this bump should lie, and it's set by the physics that is happening around recombination. If you could calculate this from first principles, and in order to do this, basically the main thing you need to know is the composition of the universe. If you were able to do that, then you have some standard ruler. Then you see you make galaxy redshift surveys at different redshifts, and you see at what angle you see this feature, and then you equivalently in the radial direction, what radial separation you see, and that serves for you to measure say the angular diameter distance to the redshift of the redshift survey, and thus map the expansion history of the universe. So this was the program of this survey, and the idea for the most part was to use the calibration that for the location from first principle, the knowledge of what's the size of this ruler was coming from Planck and the CMB. That is very good calibration, but to the extent that there is a discrepancy in the Hubble parameter that you get from the CMB from what you get directly, you might think that maybe there is something that we are not understanding. And as a result, it would be nice to get a calibration of this angular of this size that does not rely on the CMB. And it turns out that this, if you not focus only on the wiggles, but also on the broadband shape of this power spectrum, and you had a good model that you can use to make the prediction for this 2-point correlation function, you can determine the, say, the amount of dark matter in the universe just from this data, use it to compute the size of the BAO from standard ruler, and then get a measurement of the Hubble parameter without ever using the results from the CMB data. And so this is what we did. We used our technology for computing the shape of the power spectrum and the corrections and so on to determine omega matter H squared, the amount of dark matter, and then use this to calibrate use this to compute the size of the BAO, and then get that measurement of the Hubble parameter. Of course, this happens all automatically. It's not that we make this in these steps, but we are fitting a cosmological model that has all of the parameters directly to this data, and it comes out the Hubble parameter. It's not that we split it this way, but that's and here is an example of the formulas that we're using. We are, as I was saying, this is just all some sort of a perturbative analytical model. It doesn't really matter exactly what these things are, but P is the power spectrum. So it's a model for the power spectrum in redshift space, depending on the linear power spectrum and corrections to that. And those corrections are what we've, and for the purpose of the current survey, it's just the next to leading order corrections, which is what's written here as an integral over the power spectrum, so-called one loop correction is all that's required, but in the coming years, we will need to improve this. And so here's the example of those constraints that we got for the Hubble parameter. And you can see I'm highlighting there one of the panels here where there is the constraint on the Hubble parameter, and you can see here the constraint that we got from this BOSS data compared to the Planck measurement. So they tend to agree. This measurement at least gives the same result as the Planck measurement did, and not what the low redshift universe measurement gives. And the size of the error bars is the same. It's very simple. So as the Planck. So this is an application of this technology that we have been developing. In the last few years, we've tried to test our models to a little bit under the assumption of even significantly smaller error bars as a result of the fact that we are going to get bigger volumes in the near future. And so these are results of some comparison between simulations and this analytical theory. So this was a blind challenge. Somebody produced these simulations. They didn't tell us the cosmological parameters. These are volumes much bigger than what these BOSS surveys. The volume that which we are comparing this and which sets the error bars for all of our comparison was 560 cubic gigaparsec compared the BOSS volume, the actual data of today. Is significantly smaller than that. So this is much more stringent tests to see if we would recover cosmological parameters, and also to demonstrate that with the error bars that you would get, which are 10 times larger for BOSS, you would not expect to have any kind of bias in the measurements. And so this is tests that we did for the 2-point correlation function, and what we've been doing lately is looking at higher order correlation functions, in particular the 3-point function or bispectrum. So these are examples of the same tests for the 3-point correlation function, residuals between the data in these same simulations with the same volume and so on, between the data and the theory for the 3-point function. The 3-point function in Fourier space depends on 3 wave vectors. So it's so here is some examples of some choices to be able to plot as a function of just one variable. At the moment, in terms of the technology that we have used for this comparison, that we can use to map to existing data, we have only computed the lowest order bispectrum, so the so-called 3-level bispectrum in redshift space. We have not yet finished the computation of the next to leading order, the correction, which is something that we are doing now, and it's clearly needed for this kind of volumes. But we have not so much for the existing data, but yes, for the future. In the last several months, Oliver Philcox, who's a very good student and is finishing up, he has implemented the so-called optimal quadratic and cubic estimators to measure the power spectrum and bispectrum of the existing BOSS data. This is not something that is not the way these surveys are being analyzed. In the case of the power spectrum, it's not particular. There's not that much of an improvement, even though I should say that for people that are interested in in the results from the BOSS survey, the official power spectrum that they put out was computed incorrectly, and there is wrong window functions, and it gives a few percent, 5% different in the amplitude of sigma 8, which is this parameter for which there is attention. There is a recent paper fixing this by some people at Berkeley, including Martin White. One of the students, I think, is the first author, I forget. But also we agree with this. This paper just came out. We also agree with the same results. But more interestingly, is that we now have a measurement using the cubic optimal cubic estimator of the bispectrum, which is something that has not been done correctly so far at all. And cosmological constraints from the bispectrum are not, always seem to be in the future. So I'm already at 30 minutes, so let me skip this. So let me summarize by saying that there's substantial improvement expected in large-scale structured data in the coming decade. We are the next generation of redshift surveys is already operating, and it's taking data like crazy. So there's expected significant improvements. There's many questions in cosmology that we hope to answer from these and other data related to the small scale clustering, or using the clustering of matter on large scales at the late universe, broadly defined, I guess. For at least for the purpose of the galaxy redshift surveys, the situation is that we will have exquisitely small error bars, and the distribution of matter cannot be modeled with linear theory, so something better needs to be used. But still, the deviations from linear theory are small, and so we have been, embarked in a program to use various more analytical techniques rather than just trying to do forward model with simulations. And so at the moment, I think for the most part, this is the kind of model that is used to fit the data everywhere. And I think we are in a reasonably good shape. But for upcoming surveys, we do need to improve these models by going to higher orders for the power spectrum and even the bispectrum in redshift. So there's still things to be done, and also improvements in the way we measure these statistics, because it's not the state is not perfect, I would say. But as an application with current data, you can look at this current measurement of the Hubble constant that we have. Okay, so I'll stop there.
Thanks, Matías, for this comprehensive summary. Any questions for Matías? Rogerio, I see your hand first. Go ahead.
I was faster than Claudia. So Matías, thanks for the talk. And I have actually two short questions. One, can you apply this also to photometric surveys in addition to spectroscopic surveys, this method? And the second question is, in DS, we have used for the nonlinear power spectrum just a simple parameterization as halo fit. Will you think that using EFT can bring us some advantage?
For photometric redshifts, I think, this can be used for anything. Now, in general, I would say that if we are discussing some survey that has small error bars that is competitive, like the ones that you are thinking about, but they are just photometric, so they are just basically two-dimensional surveys. In order to have, they are usually having to go to smaller angular scales. so that you have enough the same number of pixels at the end to get similar constraints than the Redshift surveys. And then as a result, they are going to more nonlinear scales. And so it's not the place where this is the best, because once you go to once you approach the nonlinear scale and the corrections are not small, this perturbative expansion breaks and you cannot there's no two ways around it. And so then you have to jump to simulations. So I think, and this is the same situation, this is what's happening for weak lensing type thing. So I think that's not the best application for this technology. I think there you have to rely more on simulations and just fits to simulations. Now, things like, which is what this halo fit is. Now, for weak lensing, probably that's a little bit better than for galaxy surveys, in that at least there you are you don't have the issues or so much of bias. You're just getting the total matter, and the complication is that baryons probably move slightly different than the dark matter. So when you go to sufficiently small scales, that's a problem. But it's much less of a problem than tracing the distribution with the individual galaxies, which are completely complicated from the get-go. So
right.
Yeah.
Of course, the best thing is to combine clustering with weak lensing. That's what we do. So we break the generacies.
Yeah, this is the best. Yeah, of course, this is good. And also there's situations in which you can do cross correlations, in which you have, so you can still stick to larger scale because you're cross correlating with the Redshift survey. So for there, I think this is pretty, as long as you stick to Ks that are relatively low compared to the nonlinear scale. So at Redshift 0 would be a K of, or for around 0.2, or you can go to 0.3. If you stay in this, as you go to a little bit higher Redshift, then it's fine. This you can use. Once you want to get information away from that on smaller scales, this is not the way to do it.
Thank you very much, Matías.
Great. Cora, go ahead, please.
Yes. Yeah, thank you very much for the interesting talk. So my question is about the normalization error. First, is the normalization error just in the power spectrum, or is also in the correlation functions, which would worry me? And then
Go ahead. You mean for BOSS?
Yeah, for BOSS. And the second, this is the paper by Stephen Chen and who is the student of Martin White. Yeah.
Yes, this is the paper. Thanks.
So the second question is, I'm guessing now, after fixing for this normalization problem that was in the BOSS release, you get a more consistent sigma 8 with Planck. Is that right?
Yes, correct. So it's in that direction. The error is in this direction, so it makes it more consistent. Yes, they in this paper, they kind of point out this. I mean, they correct this mistake for sure. And I don't know, I suppose because they were part of this survey or whatever, it's not super explicit that there is a bug. But or I don't know. I think if you go to BOSS website, you still download the same thing as you were downloading before, with no warning that there's a bug. And it affected just it affected their power spectrum, not the 2-point correlation function, because it was a bug in the, maybe you want to say even the definition of the window function. So you could have, so the normalization, they were renormalizing their power spectrum by some integral of the number density square instead of the number density that was supposed to come from some window function. Incorrect. So yeah, I mean, for us it comes out that we don't have, I mean, this when you do the measurements using this quadratic estimator, you don't have, you're directly estimating the band power, so this is already taken care of internally. when you compute the Fisher matrix and all of these things. Like you don't. This issue we don't have, but right, yeah, this issue we don't have, and we agree. I think. I mean, of course. If you look at that paper, the Martin White student paper, they provide the power spectrum or the measure the power spectrum convolved with the window. We are giving you the power spectrum without the window. But in any case, if you fit parameters with their power spectrum and their window, or we do it with our thing, they lie on top of each other perfect. So we agree 100% with that. But it was a bug, so it can be traced. They know what it is. It's not, yeah, it was a mistake.
Thank you.
Thanks Matías, I have a question. If I don't see any other hands raised, so my question is a bit different. Has machine learning played any role in? I'm sure it might have any role in this kind of results, improving them, or something like that.
I think there is a very large community of people that are trying to use machine learning for different aspects on large-scale structure. I think that so far, if you were to look at the cosmological constraints of any of these surveys, they are not coming like from this type of approach. And I think for at least the redshift surveys that I'm discussing here, because it's so close to linear theory in some sense, there is not a good, in my opinion, not a good motivation for such a thing. Like you wouldn't use machine learning for doing the CMB where everything is Gaussian and you know the statistics and you write the problem and you know what you have to do. Here, it's not exactly like this, but on this large scale, it's almost like this. So I don't think there is a very big motivation. Except maybe, I mean, there's other places where there might be, for example, photometric redshifts or various other things that are, but I mean, there's a lot of effort on this, and I'm pretty sure that their application will exist, and eventually many more things will be done this way. But at the moment, I haven't seen the clear thing that is where it obviously wins against everything else.
Okay, thank you. Great. So thanks for a wonderful talk and set of questions. I think we are doing very well with time. If there are no more questions, we can move to our next